today we're going to take a look at multiplication and division of integers. And to start with, we're going to go back to the idea that we had encountered in the last chapter, or the last section of this chapter, about the chip model. And taking a look and thinking about this chip model, remember we dealt with these circles. And inside of my circle, I actually placed chips. And my chips were black if they were positive, and they were red if they were negative chips. And we have the same idea here, but we are going to actually talk about these values meaning different things. So this negative is going to mean to take away 4 groups. Hence, we've got 4 groups, and the minus is taking them away. And these are 4 groups of 3 negatives. So in order to start with this, I have to have at least 4 groups of 3 negatives inside of my drawing. And we could have other things inside there as well. There could be some more negatives, some more positives. So this is the bare minimum. And what I need to do is I need to take away 4 groups of 3. So here's a group of 3. Here's a group of 3. Here's a group of 3. And here's a group of 3. And if I've removed those 4 groups of 3, that's equivalent to having moved them. And I'm running out of space in my diagram, but imagine I have over here another circle of putting all of those and having removed them into another circle. And I have 12 items that I have removed. So there are 12 groups, or sorry, of the 12, I've taken away 4 groups of 3 for a total of 12 chips that have been taken away. The charge fields model, of course, is the same idea. So it's just that I deal with it being with, instead of removing 3 negatives, I remove 3 actual negatives instead of 3 red chips. So I have all of these, and I remove a group of 3. And so I end up again with the same 12. Another model is the number line model. To do the number line model, we're going to actually think about this in terms of distance and time. So of course, when we go left, that's negative, and when we move right, it's positive. So no matter whether you're considering the 4 or the 3, we're going to move left somehow. And we're going to treat this as though the first number is our jumps or movements. And then in this case, it's left because it's negative. So we're going to move left in jumps of 4, in groups of 4. Let's say move left 4 at a time. That'll work. Now, the second number, this negative 3, we're going to reference this in terms of time. So this would mean time starting 3 hours ago. So you're kind of thinking of it going backwards. So for instance, in the last hour, if I moved 4 to the left in the last hour, I would have started at 4, and then I would have moved 4 to the left in the last hour. But I'm supposed to do this 3 times. So an hour before that, 2 hours ago, I would have been at 8 when I moved 4 to the left. And then 4 hours before that point in time, I would have been at 12. So the 12 is my solution because I have started 3 hours ago. I was 12 to the left of 0. All right, and then we're going to take a look then at what the actual definition for multiplication does for us. And we've actually defined multiplication in terms of, or for whole numbers. So it's really the negative issue, or combining a negative number and a positive number that we're going to be looking at. So the first one is if A and B are integers, and A is negative and B is negative, then when we multiply A times B, this is the same thing as taking the absolute value of A times the absolute value of B. Hence, it becomes positive. And then the other option is either that A is negative and B is positive, or A is positive and B is negative. In other words, what happens when I multiply a negative number and a positive number together? Well, if I multiply a negative number and a positive number together, I still have the absolute value of A and the absolute value of B multiplied. But it is negative because one of my numbers was a negative number. All right, we're going to take a look at properties of integer multiplication now. This is going to feel like when we've done properties of multiplication before. The first one is closure property. So we have integers a, b, and c. Closure says that if I multiply a times b, this is a unique integer. In other words, an integer times an integer is an integer. That's closure. The commutative property, of course, says the order of the multiplication doesn't matter. Right, 5 times 3 is 3 times 5, but also we can do it with integers. So 5 times negative 3 is negative 3 times 5. Associative property says that the groupings don't change the value. So if I group A and B together, then multiply, it's the same as grouping B and C together and then multiplying by the A. I have 3 more. I have the identity property of multiplication. This number 1 was an identity before, and it's still the identity. This is the unique integer such that 1 times A equals A times 1 equals A. It's the only number we can multiply by and not change the value we're working with at all. And then the distributive property of multiplication of integers says that if I have a times b plus c, this is equal to ab plus ac, and I can do it in other order as well. So if I had, for instance, b plus c times a, I can distribute, so it's ba plus ca, which is, of course, ab plus ac, just with the commutative property here as well. The last one is zero property of integers. 0 is the unique integer such that a times 0 is equal to 0 times a, and it's back to 0. So it's a number when I multiply by it, I don't change, right? I get back the value 0 itself. All right, so these 4 problems ask us to identify the property that is being used. The first one says that negative 2 times 3, remember this number is an element of, so this is an element of I, which is the integers. That is the closure property, right? An integer times an integer is an integer. Negative 4 times 0 equals 0 is the zero property. Negative 2 times quantity 3 plus 4, and you notice that it sort of looks like that we are multiplying this negative 2 times each of the values themselves. This is the distributive property. And the final one on this slide says that if I take negative 2 and I multiply by 3, that is equal to 3 multiplied by negative 2, and that's the commutative property. Few theorems and definitions next. So theorem 5.6 says the following: if I have an integer a and I multiply a negative 1 times a, then this is simply the opposite of a, or negative a. Theorem 5.7 says that if I multiply negative a times b, this is the same as the negative of a times b. And we could prove that, or we could think through that by using the idea of the associative property and this theorem 5.6, where we've sort of separated out the negative a means negative 1 times a, and then we use associative property to show that. And then the next one is actually a variation of the distributive properties, just for subtraction times a value. And of course, the distributive property still holds. And again, we could use that and show that with the distributive property that we already have, and the fact that these are integers. Theorem 5.8. Oh, you know what? Theorem 5.8 is the one I just wrote down. Let me fix that. Let's go back and fix 5.7. I will copy these to the next screen. so that's actually theorem 5.8. Let's go back and fix 5.7 now. I apologize for that. Theorem, actually, I guess I'm combining theorem 5.7 and 5.8. All right, let me just fix 5.7 and then I'll fix 5.8. Okay, so theorem 5.7 was the first one that I did write down. Negative A times B is negative times AB. That's exactly what I wrote down before. Here is what theorem 5.7 part 2 says. Negative A times negative B. So when I multiply two integers that are negative, this is the same as the quantity AB itself. And that's a variation of how we've sort of described integer multiplication earlier on. Over here then, it's part 1 that I need to fix. Okay, so part 1 actually should be the reverse of what part 2 says. That is, it's the integer version of the distributive property of the subtraction between here. So this is AB minus AC. All right, those are fixed. And again, we can prove that just like we could prove part 2 using the facts that we have on the previous slides and properties that we have for those. All right, last thing in this section, remember, is called multiplication and division, is this idea of division for integers. This one is talking about a definition of division, much like we've seen this definition before. It says the following: if we have integers A and B, then A divided by B is the unique integer C, if it exists, such that A equals BC. And the idea here is, let's say for instance that I had 8 divided by negative 4. Well, 8 divided by negative 4 is of course negative 2, and the reason is because the negative is the 8 is equal to negative 4 times negative 2. And again, we see this happening more and more in the curriculum these days, where students are given work that looks like this as they sort of encounter multiplication and division for the first time, and they're asked sort of like this to fill in the question mark. And they say, oh, what do I multiply by negative 4 to get back 8? And they say, oh, it has to be negative 2. Oh, that means that 8 divided by negative 4 is in fact then negative 2. And this divisibility idea we've encountered once before as well for whole numbers, so we'll encounter it one more time for integers. So if A divided by B is a unique integer, then A is considered as being divisible by B. Or equivalently, we could say that B divides A. And if B divides A, the notation, remember from sections before, is we have a B, we have a straight line down A, so this says B divides A. When we work with less than, we've seen this is the exact definition we've used before for whole numbers. We have integers and A is less than B. That is true if and only if there exists a positive integer K that we can add to A to get back B. For example, remember that if we did something like negative 2 is less than 7, that is only going to be true because there is a number that I can add to 2 to get back 7, and that number namely is actually 9. So negative 2 is less than 7 because of this fact, and we can think about it like this as well. And then if we want to talk about a number being less than, another equivalent definition is if you have a number A less than B or equivalent B greater than A. This will be true if and only if B minus A is a positive integer. That is, B minus A is greater than 0. And we can take that same example that I did above. The reason we can say, or one justification for saying that negative 2 is less than 7 is because 7 minus negative 2, which is 9, is a positive number. Our last slide goes through a few facts about inequalities in terms of adding and subtracting numbers and multiplying and dividing numbers by inequalities. The first one is the addition idea. So if x is less than y and n is some number, then x plus n is less than y plus n. Just the idea that I can add a number, and it can be a positive number or a negative number, so equivalently this could have been written with subtraction. And I can add or subtract a number to both sides, and it doesn't change the direction of the inequality. Now that's different than part B, because part B says that if x is less than y, then negative x is greater than negative y. And that requires a little bit more work to think about. This is the idea that if we multiply by a negative number, it doesn't even have to be -1, we'll see in a moment, but if we multiply by a -1, it would change the direction of the inequality. And I want to give you an example of why that's true. So let's say I have 2 less than 4, and now I put a negative over here, -2 and -4. And if you take a look and think about from a number line perspective, of course, here's -2, and -4 is to the left of it, which means that -4 is smaller, and so my inequality opens to the right towards the bigger number. -2 becomes the larger number. And then again, we're going to take this idea of multiplication in one step further. So if we take this x is less than y and in a positive number, we can multiply by n, and it will not change the direction of any inequality. Now one notices then that on the second one here, this condition changes. Now I'm going to multiply by a negative number. In essence, I'm doing part B, but in general, not just by -1, but by any negative number. And if I multiply by any negative number, so I still have xn and I still have yn, but then just like on part B, the direction of my inequality changes.